So in this video, we're going to take a look at question 8 of the Chapter 5 homework. And we have a beam that's subjected to a distributed load. In this case, we're only asked to replace the distributed load by a single concentrated load. However, we could do the entire equilibrium analysis problem. It would be relatively simple because we've worked this kind of problem previously in the text. It's just that the beams in that case hadn't been subjected to a distributed load. It had just been single individual forces or concentrated loads. So we know how to do this problem overall if we can take the distributed load and represent it as a single concentrated load. So the question is, how do we do that? Well, hopefully you remember, if you want to draw a single force vector along this beam that represents the effect of that entire distribution, you'd have to know two things. You'd have to know its magnitude, and you'd have to know where to put it. And the way that you get the magnitude of the single concentrated load is to compute the total area under this distribution curve. So the ideal is that the density of the distributed force increases from whatever value of F1 you're given. I think I'm given 1200 below, up to the peak value of 1600 Newton meters. So what you want to do is compute the area under that density curve. That gives you the magnitude of the single concentrated force. And you want to compute the centroid, particularly the x-coordinate of the centroid, or how far away the center of the centroid, which remember can be equated to the center of gravity if we assume that area corresponds to a homogeneous, infinitely thin plate. So you can kind of look at it as the balancing point in just the x direction. So hopefully everyone can see that's going to be farther towards the right side than the left side because this area tapers up. If F1 were to be equal to 1600 newtons per meter, the centroid would be right in the middle. So the larger your F1 is, the closer it's going to move from the right side of the beam back to the middle. But it'll never go past the middle as long as F1 is never greater than 1600 newtons per meter. So we got to find two things: the area of this under the density curve along with the centroid of that area. So let's start by actually decomposing this into parts. We want to take a composite centroid approach like the example that was discussed in the Chapter 5 lecture. However, as I mentioned when you did that lecture, it's not wise to do it the way that the book did it, which is to break it up into two triangles. It's a lot easier, at least to me, to break it up into a rectangular base of height F1 and then a triangle that's going to have height of 1600 newtons per meter minus whatever your F1 is. So just to put numbers to this, I'm going to use the value of F1 that I was given when I generated the problem, which was 1200 newtons per meter. That means that F1 is the rectangular shape, which I'm hereby denoting as A2, is 1200 newtons per meter high, and the triangular shape is 1600 minus 1200, or 400 newtons per meter high. So pretty easy to compute the area of both of these shapes. For the triangle, it's just going to be 1/2 the base of that actual area, which corresponds to the length of the beam of 6 meters. So 1/2 times 6 times the height, which, as we said, it's 1600 Newton meters, the peak, minus the minimum value, which is 1200. So that'll be 400. So 1/2 times 6 times 400 is going to give us 1200 newtons. Remember, newtons per meter times meter will be just newtons. And it's easier to represent that, in my opinion, as in engineering notation, as 1.2 kilonewtons. So that is if the beam were only subjected to that triangular load, that would be the magnitude of the load. However, remember that it's also subjected to this rectangular portion, area of a rectangle, just width times height. So the length of the beam, 6 meters, times the height that you're given for F1. Mine was 1200. That comes out to be 7,200 newtons, or 7.2 kilonewtons. So if all I were asked were to find the magnitude of the single concentrated load, I just add these two values up, 1.2 plus 7.2, that would give me 8.4. Now, the harder part is to get the centroid. Now, you can set up your table if you want, but I think it's just easier to remember what the actual centroid means. What it means is that total shape, if you consider the rotation that it induces about the y-axis, and all moments of rotation are going to be determined by two factors: perpendicular distance from the axis, and then total weight, which really here we're, in this case of a centroid, we're proxying by the area. So the total shape, if you take its area and you multiply by the x location of the centroid, wherever that is, it has to be equal to the sum of that product for each component of your composite shape. So what I'm saying here is if you knew the total centroid, that's what we want to find. When you multiply by the total area, which gives us the tendency of that area to rotate about the y-axis, that has to be equal to the sum of those same quantities for each component of our composite shape. So we broke it into two, so we're going to sum over 2. The only question is, now we know the areas, but how do you get the centroids of these individual shapes? Let's start with A2 since it's the simple one. Since this is a rectangle, it has a vertical line of symmetry and a horizontal line of symmetry. And anytime a two-dimensional shape has two lines of symmetry, the centroid is right in the middle. So the x location of the centroid, which is all we care about here, x bar 2, is going to be the length divided by 2, which is just going to be 3 meters. So hopefully everyone sees that's where I'm getting this 3 meter value. Now remember, this is a coordinate. It has to be referenced from some origin. So I'm choosing to measure everything horizontally from the left side of the beam. So the left side of my beam is x equals 0. I'm measuring everything out to the right. So for the actual area here, for the centroid of area 1, which is the triangular area, the formula what you want to remember is from the peak base, it's always 1/3 of the way along the base. So from the side of the base that has the peak value, it's 1/3 of the way out. I think I called it the fat side of the triangle in the lecture video. So if this is 6 meters wide, I'm going to go 1/3 of the way out in order to find the centroid. Hopefully you see my mouse there. 1/3 of 6 is 2, so it's 2 meters from the right. But remember, we're referencing everything from the left side of the beam. So if it's 2 meters from the right, it's 4 meters from the left. So that's how I'm getting this x bar 1 equals 4 meters. If I take the product of the centroid of the triangle times the area of the triangle, plus the centroid of the rectangle times the area of the rectangle, and I divide that by the total area of both shapes, that will give me my x-centroid, which in my case turned out to be 3.14 meters. As expected, it's on the right side of L over 2. That is the halfway point of the beam. If F1 were equal to 1600 newtons per meter, it would be right in the middle. The smaller that F1 is, the more it's going to be shifted over to the right up to the maximum value. If you think about it, if this were just a pure triangle, right, the centroid would be, again, going from the right, it would be 1/3 of the way over. 1/3 of 6 is 2. The centroid would be relative to our coordinate system, x equals 4, if F1 is equal to 0. So if you want to rework this a couple ways, work at F1 equals to 0, you should get 4. Work at F1 equals to 1600 newtons per meter, and you should get 3.